Okay, welcome everyone to the last BPS of the semester. And it's our pleasure to have Elena Pulvirenti and Saida Murillo today. Elena's joining us from Delft and Saida's from Bonn. And they'll tell us about their joint work on metastability for the Curie-Weiss model. And as usual, we have two talks. Elena will give the first talk today, and then Saida will give the second talk. And the slides for the talks are already on the website. You can find the link in the chat. Elena, please.
Okay, thanks a lot, and thank you for inviting us to give a talk at the Bangalore Probability Seminar. It's really a pleasure for me, and I will talk about metastability for a dilute Curie-Weiss model with the Glauber dynamics, and I'm going to start with a very introductory talk, so I hope it's going to be accessible really for everybody. And then the plan is that Saida will give you some insight on some of the proofs, and she will also give an overview of what she's working now with Frank de Nollander and Anton Bouvier. So the topic that I will be talking about comes from a work in collaboration with Anton Bouvier and Saida from Bonn. They are both in Bonn. Okay, so let me start really from the beginning. So in the first part, I wanted to discuss about metastability in general. And what is the metastability? Metastability is a very widespread phenomenon which we see in many different systems. And the way one can describe it is that we have a system which is under the influence of some stochastic dynamics. And what we see is that this system moves between different regions of its state space on different time scales. This means the following, that we can recognize that there is a fast time scales where the system starts its dynamics in a subregion, and we think that it reaches equilibrium in this subregion. But what happens is that the system reaches quasi-equilibrium within a single subregion. But if we look at the system on a slow time scale, we see that after a very long time, the system jumps between a subregion, between different subregions. So the presence of these different time scales is, in a sense, is making us think that this system is metastable. And here I'm citing two monographs about metastability. One is by Olivieri and Vares, and the second book is by Anton Bouvier and Frank de Nollander, and they both deal with a rigorous approach to metastability from the mathematical point of view. And the first one uses the so-called pathwise approach, and the second book deals with the potential theoretic approach to metastability. So let us now specialize a little bit, and let's look at metastability in statistical physics. Well, we can say that metastability is somehow the dynamical manifestation of what is called a first order phase transition. So we know that, let's make an example now, the condensation. So we know that the matter exists in three different states, and here this is described by the following diagram where P is pressure and T is temperature. So we know that the matter exists in the solid, liquid, and gas phase, and these states are separated by coexistence lines. So what happens is that when you change the parameters of the systems in such a way that you cross these coexistence lines, you would expect that the system change phase. If we do the following experiment, if we start from the gas phase and we cool down the system, we should see that the system become liquid. But what instead what we see is that the system will persist for a very long time in a metastable gas phase before going to the new stable state, which is the liquid one. So this delay in the condensation process is also a metastability phenomenon. So one would like to study, say that the time that the system needs to condensate. But the point is that most systems of interest in physics have many degrees of freedom, and they are difficult to study because of that. So one strategy would be to find a way to map our systems to a low-dimensional state space, or to do a so-called coarse graining. And now I want to start with a toy model where this coarse graining works perfectly. So this case is the Curie-Weiss model. So now we are not in the context of fluids anymore, but we are looking at ferromagnet. So the Curie-Weiss model is a spin model describing a ferromagnet, and the atoms now are thought as fixed in a crystal, and they are only described by their intrinsic angular momentum, which is called spin. And because from quantum mechanics, we know that spin is a quantized quantity, it can take only two values in this model, plus and minus 1. So the context is the context of a spin model. So the setting is the following. We have n sides, and you would see that it doesn't matter the structure of the lattice we are in this moment. And I will be clear why. So the configuration space is just the space of all the possible spin configurations, which are sequences of spins which take values -1 and +1. And how do these spins interact with each other is encoded in the Hamiltonian of the system, which is this function here of the configuration sigma. And we can see that there is a linear part and a quadratic part. The linear part represents the fact that each spin sigma I interact with a certain magnetic field H, which is thought as positive and constant. All right, so this is the linear term. And what about this quadratic term? So we see that each spin sigma I interact with another spin sigma J, disregarding on their position with the same coupling constant, which is 1. So this is in fact called a mean field model, because each couple of spins interact in the same way, disregarding on their location. That's why actually we do not care about the structure of the underlying lattice they are on. And we see that we have this factor multiplying the two-body interaction term. And the reason for this is that the Hamiltonian is an energy, and the energy have the dimension of the size of the system, which is n. So H should go like n, but we know that this sum is of the order n squared. So I have to normalize with n in such a way to define an interesting system. And the reason why we have a minus here is that this is a ferromagnet. So the spins, the Hamiltonian would like the spins to align with each other. So it is an attractive Hamiltonian, if you want. So here I've put, without being complete at all, I've put three possible references to find in general the Curie-Weiss model, but there are many others. So let me say a few words about what it means to have a mean field interaction. So mean field means that the energy depends on the configuration sigma via the so-called empirical magnetization, which is nothing but the average of the spins normalized with the total number of spins. So the Hamiltonian H depends on sigma only through the empirical magnetization, which is a function which takes values in this space here. So it goes from -1 to 1, and all the time you go up by 2 over n. And the reason why the Hamiltonian depends on sigma only via the magnetization is because the sum can be expressed as the square of a sum, and then the sum can be rewritten in terms of the magnetization. So it is quite clear that the Hamiltonian takes this form here and can be written as n times a function of only m, the magnetization. Okay, so this is what mean field means, and this feature makes the system much easier to be studied, because one can observe everything through the point of view of the magnetization. So you have a reduction of degrees of freedom. Let's now, we are in the context of statistical mechanics. This means that at equilibrium, the probability that I see a configuration sigma is given by a Gibbs measure. And a Gibbs measure has a Boltzmann factor, which goes like e to minus beta times the Hamiltonian, where beta is the inverse temperature and is a positive quantity, and where z is called partition function, but it's nothing but the normalization of this measure. So the nice thing of having to deal with the mean field model is that you can define on the space gamma of the magnetizations so-called mesoscopic measure, which is a measure Q which takes values in this space gamma and is defined as the equilibrium measure computed in the set of configurations which have a fixed magnetization M. So this measure is called mesoscopic because it doesn't look at the detail of the ferromagnet of the system at the specific configuration of sigmas, but it only looks at the mesoscopic level, say, where you only have magnetizations. And it is easy to see that this measure can be written as an exponential of minus beta n times the free energy. So the free energy is a function of the magnetization, which is given by the sum of two contributions, where E is the Curie-Weiss Hamiltonian, is the Curie-Weiss energy, and defined in the previous slide actually. And this second contribution is the inverse of, well, the temperature actually, the inverse of beta times the entropy. So the entropy is the logarithm of the number of configurations of sigma, which give me a fixed magnetization M. So it's just it's the usual entropy as we know from statistical mechanics. For what follows, I will always use this notation. I will call S of M the set of configurations sigma which give me magnetization M. So I hope it is clear, this overview of what happens for the Curie-Weiss model at equilibrium. But because before I said that metastability is the dynamical manifestation of phase transition, and we know that the Curie-Weiss model has a phase transition, what we want to do is to think of stochastic dynamics for Curie-Weiss and study this phase transition dynamically. So now think of the configuration as being a Markov chain and not anymore a fixed configuration sigma. So you will have a Markov chain, say sigma t, which evolves with a Glauber dynamics on the state space S, and with beta, which is the inverse temperature. This kind of dynamics is called spin flip dynamics. This means the following, that you can go now we have a discrete time Markov chains that go from sigma to sigma prime with this probability. Let's see first what kind of transitions one can do. You have a configuration of spins, and you can flip one spin. This means that you go from -1 to +1 with probability p sigma sigma prime, which is the following. You can pick one of these spins at random, uniformly at random, and then you flip it with an exponential of -beta times the difference of the Hamiltonian's positive part. So this means that this Glauber dynamics is rewarding the flips where you go to a lower energy. So if now we remember that we have this equilibrium Gibbs measure, and this equilibrium measure is the invariant and the reversible measure for this dynamics, for this Markov chain. So we have this Curie-Weiss model, which is a mean field model, and at every every time step, one can flip one of these spins.
Lena, one question.
Yes.
So
yes.
it means that if you have a lower energy, it flips with rate 1/n.
Exactly.
And if it's higher energy, the rate is even slower.
Yes, indeed, exactly. So if you want to go to a higher energy, then you will pay a price of E2 minus beta, the difference of the Hamiltonian. So if you want to go to a higher energy, otherwise you will just flip it uniformly at random with 1/n.
Okay, thank you.
Okay, yeah. All right, so okay, so now let us remember that at equilibrium we have this mesoscopic measure uniquely determined by the free energy. So the free energy is our key quantity in order to study metastability. So let's take the free energy as it was defined in the previous slide. So energy plus entropy. And let's take the limit for n that goes to infinity. You will have a function of the magnetization, which we can draw. And we will see that it has a double well structure. Or if you want, one can find that this function has three critical points: m minus, m star, and m plus. So in this case, because the magnetic field is positive, the m minus is going to be our local equilibrium minimum, sorry, while m plus is going to be the global minimum, and m star is going to be a saddle point, or in this case, a maximum. So this is the simplest case also of metastability, because now what you want to do is you start your dynamics here, and what you see is that the system will try to exit from this valley, and then it will go back many, many times. Why does it go back many, many times? Because the system wants to be in the minimum in the minima of the free energy. So it will do many, many times up and down. And at some point, by random fluctuations, it will reach this critical point, and afterwards it will go to the global minimum. All right, so there is going to be a time which the system needs to go from m minus to m plus, say, and let's see how big this time is going to be. So from physics, one knows that this time is going to be exponentially big in this free energy barrier that the system has to overcome in order to do this transition. So let's see if we can find this, we can describe this rigorously. So tau A is going to be the heating time of the set A for the chain. And we use this notation to describe the expectation with respect to the Markov process for this Curie-Weiss model with the Glauber dynamics, and when I start from sigma. All right, so this is just notation. So then the theorem that, so this is a very well-known result. I somehow forgot to put some references in this slide, but a possible reference is the book by Frank and Anton, but there are many other references for metastability for Curie-Weiss. So this is a well-known result. So what we have to say is that we are in a certain regime of parameters where actually the system is metastable. So beta must be bigger than 1, and H should be positive but not too big. And then what we know is that uniformly in the starting configuration, which is in the set of configurations with magnetization M minus, the mean time to go to the lower valley is okay, we have this formula, which is very big, but now let's focus on the leading order term, which is the exponential term. And as I promised before, this is exponential of beta n, and n is going to infinity, times the height of this free energy barrier. So it's the free energy at the top minus the free energy at the first point, m minus. Of course, there are much more terms in this asymptotic mean heating time, but they are subleading. So we see, for instance, that there are the second derivatives taking care of the fact that taking care of how wide are actually the valleys at the beginning and on top, and so on. But this is the exponential term is the leading contribution, and is it makes the mean time exponentially big in this energy barrier. Then a second result is the so-called exponential law, which says that if I normalize this time with the mean time, this is an exponential random variable. And this reflects the fact that as I said before, I come back many times to the original starting point before doing the transition. So, okay, so this is a nice overview, I hope, on the Curie-Weiss model. And now what I want to discuss about in the second part of the talk is a randomly dilute version of the Curie-Weiss model. This means the following. Now we want to describe a ferromagnet with disorder. The setting is exactly like before. So we are still having a configuration space where all the configurations are sequences of spins on n vertices. And now the Hamiltonian of this randomly dilute Curie-Weiss model is a modification of the Hamiltonian of the Curie-Weiss, where we dilute the two-body interaction. This means that sigma I interacts with sigma j with a coupling constant jij, which is random. So jij now are a sequence of i.i.d random variables such that they are symmetric, and their expectation is equal to p, which is a constant between 0 and 1. Now, for the remaining of the talk, we will think that jij are Bernoulli with parameter p. Notice that here I normalize with this p here, just for aesthetical reasons. So don't be worried about the presence of p there. The reason why I want to normalize with p is that it is very nice to see that if because jij are Bernoulli, or no, because jij have expectation p, the expectation of this Hamiltonian is exactly the Hamiltonian of Curie-Weiss. So we are considering a dilute version of Curie-Weiss model with this random modification of the couplings between each spin, which modify the interaction between each spin, sigma I and sigma j. Okay. So now, let me give a brief parenthesis on the fact that there is a graphical representation of these configurations. And it is the following. It is so one can define an interaction graph which has the vertex set, just our n vertices, and the edge set is are all the couples where the Jij is equal to 1. So whenever, if this is I and this is j, whenever Jij is equal to 1, then I draw a link between the two vertices. Otherwise, when Jij is equal to 1, I do not put a link. So the Hamiltonian can be rewritten in this way, where now the couplings is always 1, but I am summing only on the couples which belong to this edge set. So basically, I've transferred the stochasticity from here to here. And it is suggestive because if we take Jij to be Bernoulli, then this graph is an Erdos-Renyi random graph with edge probability P. By definition, because the Erdos-Renyi random graph has a link between 2 points with probability P and has no links with probability 1 minus P. So our model, we can see our dilute model as a Curie-Weiss model on Erdos-Renyi. And of course, the standard Curie-Weiss model is a spin model on a complete graph, no? Because every sigma I and sigma j interact with the constant equal to 1, deterministic. All right, so now now that we introduce this dilute model, what we want to do is, again, I didn't rewrite all the quantities for the dilute version because they are the same as before. So we want to put discrete time Glauber dynamics, which is exactly the same as before with a different Hamiltonian, of course. And we have a new equilibrium measure, again, depending on the new Hamiltonian, which is the reversible measure for these dynamics. So imagine that now this again, this model is evolving with the Glauber dynamics, where the spins flip with a certain probability. And now, as you can imagine, the question is, what can I say about the metastable behavior of this dilute system, which has now 2 sources of randomness. One is somehow this random graph structure, and one is the dynamics. Before giving you the results, let me just spend a few words on the state of the art and on the background in general. So the randomly dilute Curie-Weiss model has been studied at equilibrium, I would say maybe first by Bouvier and Gerard in '93, where they proved that the free energy converged to that of the Curie-Weiss model when P is decreasing with N in a certain way. Then we have these results by De Santis and Guerra, where and they somehow give an exact expression for the free energy in 2 different regimes, both annealed and quenched. And they give also results on the controlling of the fluctuations for the magnetization. Then there is a more recent paper by Cabluco, Löw, and Schubert, where they prove quenched central limit theorem for the magnetization in the regime of high temperature. And here, I didn't manage to be, of course, complete in giving these references, because I just wanted to mention that there is an extensive study of the Ising model on different kinds of random graphs at equilibrium. So here, just starting to say a few: Demo and Montanari, Domers, Giardina, van der Hofstad, and so on. But what about metastability? So metastability for interacting particle systems on random graphs is an area that I would say is still not very developed, but there are quite some results. And here I just cited 2 because I think that they are closer to what we are doing in our project. And one is a result by Domers, Denolander, Jovanovski, and Nardi, where they study random regular graphs and the configuration model. So they have, again, the Glauber dynamics, but they do not take the limit when n is going to infinity, but the limit when beta is going to infinity. And then there is this nice paper by Frank and Oliver Jovanovski, Frank Denolander and Oliver Jovanovski from 2020, where they study the Erdos Renyi random graph for in the limit when n is going to infinity. And this is exactly what we are going to study. So I'm going to also compare our results. Okay, so it's time to give the result. Let me start with the definition. So I want to define something that is called last exit bias distribution. And it is a probability distribution, which is defined as the probability. So you see that it's a distribution that depends on two sets A and B and a configuration sigma. And sigma is supposed to be a configuration in a set A. And this probability distribution is the probability that I go first to B, and then I go back to A, times the equilibrium measure, with a normalization, of course. And because I'm interested in the sets where I have configurations with magnetization and minus and configuration with magnetization and plus, I'm going to use this notation. So this last exit bias distribution is a common distribution when you work with potential theory for metastability, and this is going to be clear later. While Pj is the law of the random coupling, so if you want, is the law of the Erdos-Renyi random graph. So now the result is the following. For beta and h in the regime where one has a phase transition, so beta bigger than 1 and h small enough. What I want to say is that if I look at the mean time where I start from a configuration drawn with this last exit bias distribution, the mean time that I go in the global minimum is similar, is close to the same mean hitting time of Curie-Weiss. And when I say close, it's in the following sense. This ratio is a family of random variables which are tight. So which have a probability to be between E2 minus S and E2 S, which is bounded by 1 minus E2 minus S squared. All these constants, C1, C2, K1, and K2 are known. So I'm going to discuss about these constants in the following slide. This is the content of this paper with Saed and Anton. Let me tell you a few words about these constants. So they are quite explicit, as I said before, in the following sense. So C1 and C2 are given in terms of the parameters of the systems, which are beta and H, and also in terms of this alpha and kappa, which are the following. So alpha is a quantity which depends on beta and on P, but also on the variance of these random variables. So in this case, because we have Bernoulli, it is the following quantity. And kappa is a modification of alpha, where epsilon of alpha is smaller than 0 and is a maximum of this quantity here. So it's a function of alpha again. Okay, so this is just to give you an overview of all these quantities, C1, C2, K1, and K2. And I didn't say anything about K1 and K2, but they're numbers. So I think actually K1 is 4 and K2 is 2 or something like that. Okay, so
Elena, sorry,
yes.
one question on the,
yes.
There are two expectations inside the probability. The
Yes.
denominator is a constant, right?
Yes.
There is no randomness.
Indeed, it's a constant. Yes.
And in the numerator, the randomness is because of the Erdos graph.
Exactly. Exactly.
Okay.
Indeed.
And your parameter P is fixed. It's not changing.
Indeed. Perfect. Yes. Okay. Perfect.
Thanks.
Okay. So yes. So indeed, this is constant with respect to this probability. No. So that's true. So this expectation is with respect to the dynamics, and also this expectation is with respect to the dynamics. But this expectation is still a random variable if you think of the underlying random graph. Okay. That this is a thank you for saying that, because this is a very good point actually. Okay, so please interrupt me whenever you want. I'm happy to have interactions actually. So as I said before, also De Nolander and Jovanovski work on the same model, and the result is the following. So they prove with probability that converge to 1 that the mean time, but starting from any configuration in the starting valley, so any configuration C in the set of configurations which have magnetization M-, to be precise, their mean time is exponential in this free energy barrier. So this part is the same exponential that we see that was inside the mean time for Curie-Weiss, but with a modification which is polynomial in n, and somehow they do not identify this random exponent. But what instead they do, which is very nice, is that they give a regime for the parameters, and they obtain also this exponential law, while we do not get the exponential law for our our model. Okay, so this is the comparison with the work of Frank and Oliver. And so I wanted to sorry, one other thing that I wanted to say is that they mainly use the pathwise approach to metastability, while we use the potential theoretic approach, which is the following. So the potential theoretic approach, it links the mean time with the capacity of two sets, where the capacity of two sets is defined in terms of the probability that I first go to B and then I return to A. And this is at the denominator in this key formula. And here I have at the numerator, I have a sum which involves the equilibrium measure and the harmonic function, which is a function, it's a solution of a Dirichlet problem, where I put as a boundary values 1 in A and 0 in B. So this approach was initiated by Bouvier, Eckhoff, Gerard, and Klein in 2001. And now the idea is to estimate the capacity and the harmonic function in terms of those of Curie-Weiss which are known. And one might think, yes, but why is it better to study capacities and harmonic functions instead of the actual mean time? And the reason is that for the capacity, one has variational principles, which are helping in finding sharp bounds. So a key point in order to find these sharp bounds for the capacity is the following result, which we proved taking some ideas from Talagrand, and the proof is going to be discussed by Saeda in the next talk. It is a concentration inequality, and in the form which is written here, it was not the same as the one that we have in the paper with Anton and Saeda, but it is in the form of the ongoing project of SAIDA with Anton and Frank. I want to specify this, but I'm going to use it because for the sake of a small computation that I want to show you afterwards is going to be easier. So it is a nice result because it says that with the usual probability being bounded from below by these, we have these sub-Gaussian tails in a sense, all the time that I take any function of sigma and I multiply it by E2 minus beta, the difference of the Hamiltonians in the dilute and in the Curie-Weiss model, this sum just goes like this sum times some constant E2 alpha. All right, in the usual sense, in the usual probability sense. Okay, and this is very useful, and a direct way to use it is to find a mesoscopic measure for the Curie-Weiss, for the dilute Curie-Weiss model. So now remember what is the mesoscopic measure. Disregard, do not care about this z because it's a number, it's a normalization. This measure is the sum of the equilibrium measure over on the all the configuration sigma with the fixed magnetization m. Now, if I sum and subtract by the expectation of the Hamiltonian, which is nothing but the Hamiltonian of Curie-Weiss, and I choose G of sigma to be exactly e to the Curie-Weiss Hamiltonian for all the configuration sigma which have magnetization m. And recall that the mesoscopic measure for Curie-Weiss is, again, we have the energy part and the entropy part. Then I just apply the concentration inequality and I obtain a closeness between the mesoscopic measure and the mesoscopic measure of Curie-Weiss in the usual sense. So this is a direct consequence of the concentration. Already at equilibrium, these two systems are close in this sense, in the sense that one can control the tails. And now the question is, how can I use this concentration inequality to have a control of the capacity? As I said before, the capacities, in order to have capacity estimates, one can use variational principles. So the first result which we use in order to compute this mean time are, again, closeness of the capacities in the Curie-Weiss model and in the diluted model. In the usual sense, this ratio is a family of random variables whose tails are controlled. So it is, or if you want, this is a sub-Gaussian, a family of sub-Gaussian random variables. The proof goes like that. You, as I promised before, one can use variational principles, and you get upper bounds via Dirichlet principle and lower bound via the dual principle, the Thomson principle. Let me give you shortly an overview of these two variational principles. The Dirichlet principle is the following. The capacity is the infimum of the Dirichlet form, and this is the Dirichlet form for our model, where the infimum is taken over all the functions which are 1 in the starting set and 0 in the target set. In this way, one can get an upper bound on the capacity, and one can get a lower bound on the capacity with the dual variational principle, which is the Thomson principle. But now the supremum is over the space of all unit flows from A to B, and unit flows are maps from the state from the set of all the pairs where I can actually make a transition to, and they satisfy the usual electric networks laws, the Kirchhoff law, and which is telling me that the total flow out of a node X is equal to the total flow entering in the node X, and the total flow in entering in A is equal to the total flow exiting from B. So I think this is called in physics that A is a source and B is a sink, or vice versa now, I don't remember. But these are the usual laws of electric networks. And in this way, with the Thomson principle, we obtain lower bounds. Now, I think that I'm going a bit over time, but if I have one extra minute, I can maybe show you how to compute capacity estimates with concentration inequalities. Do I have 2 more minutes?
Sure, yeah. You can take a few more minutes.
Okay, so let me show you a very quick computation in order to see how one can get an estimate over the capacity in terms of the capacity of Curie-Weiss. Okay, so I write now the definition of capacity. All right, I will use the following notation. So sigma tilde is going to be is going to denote all the quantities of Curie-Weiss, just to have a shorthand. So what I do is that I multiply and divide by mu tilde and p tilde, which are the same quantities, but for Curie-Weiss. Let me leave this difference of functions as it was. And now I have mu of sigma, p of sigma, sigma prime, and I have to divide by mu tilde, p tilde, right? Okay, now let's look at this term here. And because mu is E2 minus beta h, I write this ratio of mu in the following way. But I have also to remember that there are these normalization constants. And then this ratio of P, I use a very rough bound, but it is enough. And I say that this is smaller or equal than e to 2 beta 1 plus h for every sigma and sigma prime. So it is a rough uniform bound on this quotient. So then I rewrite this expression in the following way. Let me bring outside all these constants. And basically, I can rewrite it in the following way. Where I have defined G as this quantity here, G of sigma. But you see that now this is exactly in the form as is required to use this concentration inequality. So this is going to be smaller or equal in probability, and I'm going to say in a second what I mean by that, with E to S plus alpha, sum of sigma, G of sigma, where I'm using the following notation. A is smaller or equal with PS of B, if and only if the probability J that A is smaller or equal than B is bigger or equal than 1 minus K1 E2 minus K2 S squared. This is a notation. Okay, now let me rewrite what G was. And then we see what I got with this quick computation. G was the sum over sigma, mu tilde sigma, sum of sigma prime, p sigma sigma prime, and the difference of the function in sigma and sigma prime. I forgot the minimum. So sorry, there was a minimum over F, which I forgot. And you see that if you put the minimum here, then this is exactly the capacity of Curie-Weiss. So I got a bound in terms of the capacity of Curie-Weiss with this concentration inequality. So this was just to show you how to use the concentration inequalities. Let me skip 2 slides to go to the conclusions and to related problems. So, these are ongoing projects and which are related to this problem. So the first one, together with Johan Dubeldam, Vincent Lenz, and Martin Slovik, we are working on the dilute version of the Curie-Weiss Potts model, where now the spins are taking Q values. Then with Saed and Martin Slovik, we are working on a dilute Hopfield model where the coupling is given by an inner product of vectors which are called patterns because they represent somehow the memory in our brain. And in the talk of Saeda, she is going to talk about inhomogeneous random graphs. And this is a project with Anton Bouvier and Frank de Nolander. And sorry for going over time. I will thank you for your attention.
Thanks, Elena, for the interesting talk. So we'll take a short break, but any questions for our speaker before we go on the break?